In this video, I'm going to talk about areas and lengths in polar coordinates. This is you can review 10.4, and I do recommend you read that section. The formula 1 below follows the fact that the area of a sector is proportional to its central angle. We know that the area of a circle is pi r squared, right? But in reality, the sector we're talking about is theta pi over 2, right? And so when theta is 2 pi, then this just becomes pi r squared. So here is your sector, and when you simplify it, we just get 1/2 r squared theta. Okay, so here's a sector. R is the region here in figure 2, bounded by the polar curve r equals f theta. And by the rays theta equal to a and theta equal to b, where f is a positive continuous function and where b minus a is less than or equal to 2. So we're going to divide that interval a to b into subintervals, right? So the endpoints theta 0, theta 1, theta 2, all the way to theta n, and then we're going to have equal widths of delta theta. So yeah, the next slide, here it is. And so we're really just cutting this region into smaller regions, which is delta a sub I. All right. And what we have then is every delta a sub I is about 1/2 r squared, this function of theta I star squared delta theta. So again, here's your delta theta. Your f theta I is here. So we're just going to plug it in and do the summation of all those smaller areas, those smaller delta A's from 1 to n, and you'll notice where we're heading here. So as n approaches infinity, we now have this general formula for area of R. So area equals the integral of 1/2 f theta squared d theta from a to b. Alright, so we could just replace that f theta, that polar function, with r, and it simplifies down to what we have here, right? Because r is equal to f theta. All right, let's do the example. So we want to find the area enclosed by one loop of 4-level rose curves. So that the rose curves are going to this form: r equals cosine 2 theta. All right, so here's our solution. Here's our rose curve. We've got 4 petals. We just want to find one loop, right? So all these loops are going to be equal. So we're going to pick a loop, and we understand that theta runs from negative pi over 4 to pi over 4, right? So we're looking at that region. So just plugging it into the equation, we take the integral from negative pi over 4 to pi over 4. This is cosine 2 theta. We're squaring that. We can pull the half out, and we go ahead and just complete that integral. All right. So we're going to get pi over 8 being the area of that one petal. All right, moving on to arc length. What we're going to do is have these parametric equations, x equals r cosine theta and y equals sine theta, as theta being the parameter for those parametric equations. We're going to review 10.2 in the next section. So and it's going to have parametric equations, and a lot of this stuff is going to be reviewed then. But we'll just quickly go over this. We're going to use the product rule, differentiating, using the fact cosine squared plus sine squared equals 1. Okay, and we end up getting this. And this equation for length, this arc length, that is, again, that's going to be in 10.2. I think that's 0.5 actually, theorem. So we're using that length theorem, plugging in the values we determined from here, and we end up with the arc length of the curve, or the polar equation, all right, which is square root of r squared plus dr d theta squared d theta from a to b. And then simply we'll go through an example. We've got this cardioid. I forget exactly what that looks like, but anyway. So what we're going to do is find the length of this. Right. So we're using our equation. We're taking it all the way from 0 to 2 pi. So here it is, 0 to 2 pi. Plugging in r, dr d theta. Okay, so the derivative. And we're going ahead and doing the integral, which isn't done for you here. You will end up with actually L equaling 8. Right, so your homework for this week will have you go and complete 2 examples, an area and a length example.